Introduction. Welcome to Module 4. In this session, we will explore the integration and economic viability of microalgae in aquaculture. We will cover why microalgae are important, how they are applied, the challenges, costs, and returns. We will also look at their role in circular aquaculture and future innovations. Part 1: Why microalgae in aquaculture? Microalgae are nutritional powerhouses. They provide high-quality proteins and essential amino acids. They are rich in omega-3 fatty acids, including EPA and DHA, which are vital for fish health. They supply important vitamins such as vitamin B12 and vitamin E. They also contain antioxidants like carotenoids, which reduce stress in aquatic species. Beyond nutrition, microalgae offer functional benefits. They boost immunity and enhance pigmentation. For example, astaxanthin from algae gives salmon and shrimp their attractive red color. They also improve feed conversion, meaning fish grow more efficiently with the same amount of feed. Microalgae also support environmental sustainability. They reduce the need for fish meal and fish oil, which are taken from wild fish. By doing this, algae help reduce overfishing and protect marine ecosystems. Examples include Nanochloropsis, which is valued for its high EPA content, and Haematococcus pluvialis, which produces astaxanthin. Part 2: Applications in aquaculture. Microalgae can be used in three main ways. First, direct feeding. Species like Isocrasis, Tetraselmis, and Chaetoceros are ideal for bivalves and shrimp larvae. They promote larval development, shell formation, and higher survival rates. Second, indirect feeding through bioencapsulation. Microalgae enrich live feeds such as rotifers, copepods, and Artemia. These live feeds then pass on DHA, pigments, and nutrients to fish larvae. For example, Artemia enriched with Schizochytrium improves sea base growth. Third, as feed supplements. Powdered spirulina and chlorella can be added to formulated pellets. They boost coloration, improve immunity, and support gut health. Part 3: Challenges and considerations. There are also challenges when using microalgae. Palatability can be an issue. Not all species of fish and shrimp accept all algae types. Digestibility is another challenge. Some algae, like chlorella and Cenedesmus, have very tough cell walls. These require processing such as bead milling or enzymatic hydrolysis. Consistency is also critical. Algae cultures can be contaminated by unwanted microbes or even toxins. Scalability brings further challenges. Large production systems require climate control, carbon dioxide regulation, and constant monitoring. Finally, cultivation systems come with trade-offs. Photobioreactors are expensive but highly controlled. Open ponds are cheaper but have higher risks of contamination. Part 4: Economics, CAPEX and OPEX. Economics are shaped by capital expenditure, or CAPEX, and operational expenditure, or OPEX. For CAPEX, the biggest decision is the cultivation system. Photobioreactors cost more but give better yields and control. Open ponds are cheaper but less reliable. Harvesting technology also adds to CAPEX. Centrifuges, membrane filters, and spray dryers are effective, but each increases cost. For OPEX, energy use is a major factor. Lighting, aeration, and temperature regulation consume significant power. Nutrient inputs are also required, including nitrogen, phosphorus, trace minerals, and carbon dioxide. Labor is another expense, since skilled staff are needed for monitoring, harvesting, and quality control. Part 5: Returns and values. Despite the costs, microalgae bring strong returns. First, they create cost savings. They reduce reliance on expensive fish meal and live feeds. Wastewater-grown algae can further cut nutrient costs. Second, they add value. By improving survival and growth, they increase return on investment. They also enhance pigmentation and health, giving seafood a premium appeal. Third, they open access to premium markets. Consumers increasingly demand seafood that is sustainably fed. Omega-3 enriched fish command higher prices. For example, salmon fed with algae-derived DHA can be marketed as eco-friendly and healthier. Part 6. Integration with circular aquaculture. Microalgae are also central to circular aquaculture systems. They treat wastewater by absorbing nitrogen and phosphorus. They turn waste into valuable biomass. This biomass can be reused as aquafeed, biofertilizers, or even biofuels. Algae also capture carbon dioxide, helping offset emissions. A good example is Chlorella vulgaris. When grown in wastewater, it both cleans the water and produces biomass that can be converted into biodiesel. Part 7. Innovations and Future Outlook. Looking ahead, innovations are making algae production more efficient. Green bioprocessing methods use solvent-free extraction, such as supercritical carbon dioxide. Genetic engineering is creating algae strains with higher yields, stress tolerance, and improved nutrient profiles. Automation and artificial intelligence are also being applied. These tools allow real-time monitoring and predictive harvesting. Carbon capture integration is another trend. Algae farms can be located near factories or power plants to recycle their carbon dioxide emissions. A new development is AI-driven photobioreactors. These systems automatically adjust growth conditions to maximize productivity with minimal human input. To conclude Module 4. Microalgae integration in aquaculture offers nutrition, functional benefits, and sustainability. They can reduce feed costs, improve survival, and open premium markets. But challenges in palatability, digestibility, consistency, and scalability must be carefully managed. Balancing costs and benefits is essential for economic viability. With new technologies, genetic tools, and AI-driven systems, the future of algae in aquaculture is bright. Microalgae are not just an add-on. They are a cornerstone for building a sustainable, efficient, and profitable aquaculture industry.